We are Robotics for Space Exploration with the University of Toronto.
We have made many significant overhauls for our rover for URC 2026.
For this year's chassis, we decided to use a carbon fiber baseplate with a single integrated software electrical module to save on weight and complexity. The module is constructed from carbon fiber tubes, which allows us to create a lightweight frame that also enhances structural integrity from last year's extruded aluminum design.
For the suspension system, we have kept last year's four-wheeled rocker system with the differential bar at the back of the rover. We plan to upgrade the differential bar to a truss structure, ensuring reliability in rough terrain. The rocker is made from carbon fiber tubings and pivots, with a steel axle. This design has allowed us to achieve a lightweight, compact, yet strong and robust design.
The wheels are 3D printed in two parts with an outer layer made from TPU with a gyroid pattern to evenly distribute deformation, and an inner rim printed in PLA+. This design and method of manufacturing has allowed rapid prototyping so that we can optimize durability and ideal absorption in rough terrain.
This year, our electrical system is controlled with an STM32 microcontroller that allows the base station to monitor and operate the electrical system over the network.
Our GUI can turn buses on and off to remotely power cycle rover devices like the motors. The custom power distribution panel can provide voltage and current monitoring to the base station. Our in-house design converters gives us a lightweight solution to the various voltages in our system. In addition to our physical e-stop mounted on the rover to disconnect power, our base station can also remote e-stop over the network and is easily accessible through the GUI. This year, we developed a lighter and cheaper custom battery management system to relay battery voltage and state of charge to the base station and provide under-voltage protection for the battery.
Our software autonomy stack is built on ROS2 Humble and is structured around a centralized state machine that manages planning and mission execution. We upgraded our onboard computing architecture from an AMD Bealing paired with an NVIDIA Jetson Xavier to a single NVIDIA Jetson Orin, significantly enhancing our onboard computational abilities. For perception, we upgraded our custom user interface, which monitors the rover's pose and camera feeds by adding mission status tracking. We begin each mission by navigating to a designated GNSS coordinate using fused GPS and odometry data to compute and traverse a global path toward the target waypoint.
We implemented a hierarchical obstacle avoidance framework. A global planner uses SAR search over a terrain cost map to compute an optimal path, while a local planner performs real-time obstacle avoidance and trajectory refinement, allowing the rover to adapt dynamically to environmental changes. Our object detection model was retrained to improve robustness under varying lighting and terrain conditions.
If a target is not immediately detected, the rover initiates a grid-based local search pattern around the waypoint to search the surrounding areas. Once an Ruko tag is detected, the rover enters homing mode, using pose estimation to guide its approach. If visual contact is lost, it retains the last known pose and performs reacquisition. All modules communicate using ROS2 DDS protocols, enabling wireless communications between rover and base station at distances up to 500 meters for stable telemetry and data streaming.
This year, ARM has undergone a complete redesign, implementing a fully harmonic gearbox drivetrain, resulting in zero backlash, in addition to a new lightweight custom carbon forging method. This is all whilst keeping the same mobility and strength, allowing us to lift more than 5 kilos. We researched and designed compliant fingers for our grippers this year that maximize surface area contact with objects, acting synchronously with our new 3M high-friction outer layering to improve arm dexterity, minimizing the required gripping force. The precision of our new zero backlash harmonics and limit switch homing system is complemented by the accuracy of our inverse kinematics algorithm, allowing for intuitive and accurate piloting.
Our code makes full use of the zero backlash system using Move It 2 packages for 6 degrees of freedom controlling Cartesian space and intelligent path planning. We combine this with our computer vision algorithms to autonomously complete tasks such as keyboard typing.
This year, the science team has redesigned key payload elements to improve integration and field readiness. The science team has developed our own end effector that works in conjunction with ARM for drilling. Soil handling is done with the gear-driven sorting mechanism that enables storage of cache sample and surface samples for further testing. Additionally, the end effector is equipped with an electromagnet to pick up and drop our temperature and humidity sensor. The primary sensor in our fluorescence detection system has been upgraded from a photomultiplier tube to a mini spectrometer, making it easier to detect green fluorescence from possible flavin molecules in the environment, indicating signs of life.
Chemical analysis has been expanded for starch detection with iodine assay alongside nihydrin for amino acid detection, producing visible color change monitored by onboard camera. Finally, our multispectral imaging system makes a comeback from last year, helping us capture multiple wavelength bands to support mineral identification.
This year, we designed our first ever drone. It is a custom 17-inch rotary wing UAV to assist in delivery mission. It's capable of stable flight using IMU, GPS, and a magnetometer, carrying heavy payloads for about 20 minutes. An onboard digital camera allows us to read signs at a long distance from base station, and a gripper allows us to pick and place objects. All systems are being tested and tuned in a custom-built test rig.
We are ready for URC 2026.